Hello, my name is Steve Bowler, and in this video what I'm going to do is be configuring RIPv2. We're going to be taking a look at RIPv2 Authentication and also the way RIPv2 finds the best path through the network, which is hop count. So what we can see in this lab is we have two end routers, router 0 and router 7. Router 0 is advertising the 150 networks, and we have on the other side of the network router 7, which is advertising the 170 networks. And what I've done so far is I've configured all the interfaces and all the routers are up already. So now what we need to do is just go in and enable the RIP routing protocol on the routers. We're going to go ahead and start with router 7. Under global configuration, to enable RIP, we're going to do the command router space RIP. And then under here, what you can see is that we have a lot of options. Under RIP, we advertise networks into RIP using the network statement. On router 7, we're going to be advertising the loopback interfaces, which are 170.0. Actually, first, what I should do is show you that we are going to be running version 2 in this lab. Version 2 is going to allow us to configure authentication between RIP neighbors. It will also allow us to advertise subnets within our RIP version 2 updates. In version 2, RIP we will see is a classless routing protocol, whereas version 1 was class full. We're going to do the no auto summary command, so we won't be summarizing the networks in the class full network boundary. Now what we can do is go ahead and configure our networks that we're going to be advertising into RIP. In this case, both of our loopback interfaces, which are 170.0.1.0 and 2.0. The next thing that we need to do is advertise our directly connected networks into the RIP routing protocol, which is the serial interface and the fast Ethernet, which are the networks 192.168.57.0, which is the connection to router 5. And then we want to do 192.168.27.0, which is our serial connection to router 2. Now that router 7 is done with the initial config for RIP version 2, we're going to go ahead and go for router 5. And all we're going to do on router 5 is advertise our directly connected interfaces into RIP. So we're going to go again to get into RIP. Router RIP is the command. We'll do version 2. We'll do the command no auto summary, and then we're going to advertise our directly connected networks, which are 192.168.57.0 and 192.168.45.0. As we can see in the lab, the way I designed the network, all the routers are using the 192.168 subnet range between each other. From router 1 to router 2, we have them under the 12 network. That means from router 1 to router 2, we're just doing the 12 network. From router 2 to router 7, we're doing the 27 network. So it just makes it easy to see where these networks are being defined as. So just an easy way to design your network if you're just using router 1 and router 2, router 3, and so forth for your router names. If I do a show IP protocols now on router 5, So a good way to determine what we can see that we have updates being sent out every 30 seconds. We also see that we are routing for the two networks. These are the networks that we advertised into RIP using the network statement. Then you can also see the interfaces, Fast Ethernet 00 and 01 under there as well, in which we are running RIP version 2 on. If I do a show IP route, the capital R for code stands for RIP, and what you can see right away, we can see the two loopback interfaces off of router 7. So we can go ahead and try to verify that we have reachability by just doing a simple ping test, and you can see we have reachability to both of those loopbacks on router 7 from router 5. Okay, so let's go to the next router. We'll go to router 2. We will enable RIP by doing router RIP. We will enable version 2. We'll do the no auto summary command, and then we're going to go ahead and advertise our directly connected networks, which are in this case the 12 network and the 27 network. So that should be it for router 2. Next, we're going to go ahead and go into router 4. We will do the command router RIP again from global configuration mode. Under RIP, we'll specify version 2. We'll do no auto summary, and then we will advertise our directly connected interfaces into the RIP routing process. In this case are the 45 network and the 34 network. Next, we're going to go to router 1. Again, from global configuration mode, we'll do router RIP version 2. We'll do no auto summary, and then we will specify our networks to advertise, which are in this case our directly connected networks, the 12 network and the 10 network. Again, 12 is the connection to router 2 and the 10 network is the connection to router 0. Next we'll go into the next router here, which is router 3. We're going to enable RIP version 2, no auto summary, and advertise our directly connected interfaces, which are the 34 and the 30 network for router 3. Now we will do the last router, which is router 0. We'll go under RIP. We will do version 2. We'll do the command no auto summary. As you can see, this is getting pretty common, pretty easy to configure the basics of RIP. Again, we're going to configure the networks 30, which is the fast Ethernet going to router 3, and the 10 network, which is the connection going over the serial interface to router 1. The next networks that we want to define under advertising into RIP are the loopback interfaces, which are 150.0.1.0 and 150.0.2.0. If I do a show IP protocols from router 0, you can see that I am routing for networks 150.0.0.0 and the 10 network and 30 network for the 192.168. So it looks like we have configured router 0 correctly. Next, what we're going to do is show you how RIP calculates its best path through the network. As you can see, we have two paths from router 7 to router 0. I have the path that goes from router 1 to router 2 to router 7, and then we also have a path from router 3, router 4, router 5 to router 7. So as you can see, we only have 3 hops to router 7 using the serial connection. And then you can see we have 1, 2, 3, 4 hops to router 7 via our fast Ethernet connections. So if we were just going to go on bandwidth alone, we would probably want to route via the fast Ethernet network, because these are 100 meg connections, as where these serial links are T1 links. So the preferred method, of course, would be to go over the higher bandwidth links. So you would think if RIP was using bandwidth as its metric, it would use its path through router 3 to reach the 7 networks instead of router 1. However, what we're going to see is not that option. RIP does not use bandwidth to calculate best path. If we do a show IP route on router 0, we can verify this. We can see the routes learned to the 170 network, which are the loopbacks off of router 7, and they are both being learned via serial 10. What I also want to point out is here we have the administrative distance for RIP, and we can also see past the / we see a 3, which is the hop count. How many hops? So there's 1 hop to router 1, another hop to router 2, and then the 3rd hop is router 7 to get to these directly connected RIP routes off of router 7. So what we can see is RIP has chosen the path with the least amount of hops. Because if we were to have gone to router 3 to get to those networks off of router 7, it would have been 4 hops to get to router 7. So again, this further solidifies our belief that RIP uses hop count to find the best path through the network. Because if it were to use bandwidth, then obviously it would have gone the lower path through the fast Ethernet. And as we can see, it chose the slower network path via the serial links to get to the loopback interfaces off of router 7. A much faster route existed via the lower network, via the fast Ethernets, but it did not choose that. Because again, RIP uses hop count to calculate best path through the network. So now we see how router 0 gets to the 7, the loopback interfaces off of router 7. Let's go ahead and do a trace to 170.0.1.1, and then let's go to router 7 and see how it finds its way to the 150 networks off of router 0. On router 7, if we do a show IP route, we can see that it is learned and has the 150 networks in its routing table. We see the RIP administrative distance of 120. We also see the hop count of 3 as the RIP metric. And these routes are being learned across serial 10. So again, it's taking the T1, or the serial link, to get to the 150 networks instead of the faster path, which would be the fast Ethernet network. just again to make sure that if we go to router 5, if we do a show IP route, we can see that it learns the 150 networks over the fast Ethernet from router 4. So those routes are being sent from being propagated through the fast Ethernet network to router 7. However, router 7 is choosing to get to the 150 networks via the lowest hop count path, which is via router 2 from router 1 to router 0. So if we go back to the trace that we set up on router 0, we have 3 hops. It sees the connection to router 1, which is the 10.2 IP, which is router 1's serial interface. Then it sees another hop from 12.2, which is router 2's serial interface between router 1 to router 2. And then it sees the last hop here, which is the link between router 2 to router 7, which is the 27.2, which is router 7's IP address. So again, that's how RIP finds the best path through the network via hop count. Again, RIP version 2 and RIP uses hop count to find its best path through the network, and a lot of people don't like that because it uses hop count over bandwidth for its metric, which is not preferred in a lot of networks. Okay, so next what we're going to do is we're going to be configuring some RIP version 2 authentication. We're going to show you between router 1 and router 2, we're going to show you some authentication within RIP version 2 and how to configure it and verify the implementation of RIP version 2 authentication. So let me just go ahead here and get set up. So on router 1, if I go under, there's 3 things that we need to configure for RIP version 2 authentication. We have what's known as the keychain, and within the keychain we have the number of the key that we are configuring. Then we have the key string, which is the actual password. So again, the keychain is what defines the grouping of the keys and the key strings. So you can have multiple keys, you can have multiple keys set up to authenticate with a remote router for added security. So you can have more than one key in this case. So what we're going to do in this case is we're going to configure one keychain with one key and one key string for this example, but you can get more. You can do more if you choose. If we go under global configuration mode and do the key space chain, and then we do a question mark, you can see that it's going to ask us for the word of our keychain. In this case, we'll make it simple and we'll say the name is 2_R2, and then it's going to ask us for our key identifier, which is, we'll just put key 1, and then under key 1 is where we will put our key string, which is which is going to be the password in this case. So what we're going to do is put in our, again, we're just going to put in our password under the key string. We'll leave the password, in this case we'll just have the password as Cisco, and if we do a show run on router 1, what we see is we have a keychain that we have created, which is 2_R2. We have one key defined, which is key 1, and then we have the key string, which is the actual password itself that is set to Cisco. Again, we can see that it is set to plain text, so anybody can see this if they do a show run. Okay, what I did was I paused the video, I went back in and enabled service password encryption, and now if I scroll down here to our keychain, 2R2, you can see that our key string has now been scrambled. So what we needed to do again was just put in service password encryption so that you're not allowed to see, no one is allowed to see the password for the key string. So now let's go ahead and set the authentication. On router 1, the interface connecting to router 2 is serial 11. We will do the command IPRIP authentication. First, we're going to specify our keychain, which is 2_R2. And that should be it. So now if I go to R2, and do a show IP route, if we do a debug IP RIP, we can see that we are getting some packets that are saying ignored v2 packet from 192.168.12.1, which is router 1, because of invalid authentication. It's updating its database. It's building the new RIP table and updating the routing table or the RIP database. If we do a show IP route on R2, we can see that we are receiving. Let's go ahead and take off the debugging command. And from R2, if we're not authenticating with router 1, that means we have to go through router 7 to get to the 150 networks. What we can see now on the routing table on router 2, we are seeing that now the networks are possibly down. Beforehand, these networks went from R0 to R1 to R2, but then we configured R1 for authentication. However, we have not done the same for R2. So R2 is seeing these routes possibly down, and this is what we're going to see with RIP if you might have a RIP problem in your network. You can see these networks are still showing up as being RIP routes in our routing table, but we have connectivity issues, so that's why these networks are now saying that they are possibly down. So now you can see that RIP has reconverged completely over using the serial 1-1 connection to router 7. So now we see the hop count is 5. So if we count the links to router 0, it goes to router 2 to router 7, that's 1. To router 5 is 2. Router 4 is 3. Router 3 to router 0 would be the 5th hop count. So we can see that RIP has reconverged across the network via its alternate path to the 150 network. Again, if you see that possibly down, give RIP some time. It's got to flush those networks out of the routing table after the hold down timer has expired, which can take a while with RIP and the default timers. So now if we do from R2, if we try to trace the 150 network on R0, the other thing that we have to remember with our keychain from router 1 to router 2 is that this keychain is in plain text. This is not a secure authentication method. What we're going to do next, after the plain text authentication, we're going to go ahead and configure MD5 authentication. So what we can see on router 2, it's going from router 2 to router 7 to router 5, router 5 to router 4, then router 4 to router 3, which is the 34 network, and then router 3 to router 0, which is router 0. So now we're seeing 5 hops in the routing table instead of 2 hops before. So let's go ahead and set up on R2. We will do the keychain. Now the keychain doesn't have to match on both sides, but the keys do. So the keychain will just do 2_R1. We'll do the key 1, then we will do the key string of Cisco. Again, key strings have to match. So now if I do a debug IP RIP, let's see if we can catch any good information. We're seeing v2 updates out serial 1-1. Again, this is the way that it's converged through router 7. We're seeing the ignored v2 packet from router 1. So we just configured authentication, so we should see this converge shortly. And as we can see, it looks like it's still ignoring version 2 packets. If we do a show run on router 1, we can see the keychain to router 2R2. Oh, you know what we forgot to do? Good thing here to show you guys. We forgot to, what some of you might have already figured out, is we forgot to apply the key string to the interface. We need to configure this under the interface serial 10, which is the connection from router 2 to router 1. Again, we apply this to the interface with the IP RIP authentication keychain command, and then we just put our keychain name, which is 2R1. So now if I go back in and do a debug IP RIP, let's see what happens. We are still receiving these networks via 5 hops from router 7. Okay, now we can see that we are receiving an update from router 1. So it looks like we've rebuilt the RIP neighbor relationship, and we've rebuilt the RIP database. If we do a unall, take debugging off, we have received these version 2 updates from neighbor router 1. I'm sorry, yes, we have received these version 2 updates from router 1 because the keychains, or the keys, now match up on both sides. So now we see the 150 network reachable via 2 hops, which was accessible when that link was, when the authentication mismatch was there, it was 5. So we can see the flash updates within RIP version 2, and it is building the new RIP database and adding these RIP routes to the router's routing table. So now if we do a show IP route, we can see that they are the RIP domain is now reconverged back from going from R2 to R1 to R0 to reach the 150 networks. So again, now these two routers are authenticating to each other, but these passwords are being sent via plain text. We can configure a stronger authentication mode via MD5 authentication for RIP version 2. Again, this is one of the advantages to RIP version 2. If we go under interface serial 10, we're going to take off the authentication that we have between router 2 to router 1, and then we'll go back to router 1, we'll go under interface serial 11, which is the connection to router 2, if I can find it here. We'll do the command no IP RIP authentication keychain 2_R2 and then hit enter. Now what we can do is use the same keychains that we made and created before, but what we can do now is make this connection between router 1 to router 2 more secure. So instead of it being sent via plain text, we can make it sent with MD5 authentication. We'll do this with the IP RIP authentication mode command, and then we are going to specify MD5. Then we also want to put in the command after we do the command IP RIP authentication mode MD5, the next command that we want to do is the IP RIP authentication keychain 2R2. Let's do a debug IP RIP events on R2 and see if we can catch any good information. Again, we should not see anything right away because of the default RIP timers. RIP takes a little while for these routes to be flushed from the routing table, but we can see already that we're getting invalid authentication messages from R1. So the next thing we want to do on router 2 is we want to go under the serial interface to router 1, which is the interface serial 10. Again, this is the interface to router 1. We'll turn off debugging. If I do the command do show IP route, we're still seeing the routing table prefers the connection via R1 with the 2 hops because we have not reconverged yet. Let's see what happens if I try to do a trace to the 150 network and see what happens from R2. So what we've done so far is we have changed authentication. We've configured authentication on router 1 for MD5, and we have not yet configured authentication on R2. It looks like it has worked so far. The trace went through. If we go to router 1 and verify that we have the keychain correct, and we also have the RIP authentication commands under the interface, now we got to remember that RIP takes a long time to reconverge, so it could just be that the protocol has taken a while to reconverge, and you can see this with the command under the routing table. If you're seeing this, you see the networks, and then you see after that is possibly down. So even though your traces might still go through and your pings might go through, after your hold down timer is done expiring, these routes are going to be flushed from your routing table and going to be updated. So I just wanted to show you guys that, just in case you've never seen that before. If we go under the interface serial 10, we'll give the IPRIP authentication mode MD5. Before, we were just using plain text between the two neighbors, which can be sniffed and could be a security threat in your network or a security risk. If we do IPRIP authentication mode MD5, it's going to make it a more secure connection between the two routers. And then we're going to follow that up with the IPRIP authentication keychain, and then we specify our keychain here, which is 2_R1. So now let's do a debug IPRIP and see if we can catch any valid or any good information within RIP. If I do a show IP route, you can see that it looks like we're seeing the RIP routes through router 7, which is the hop count, which gives us a hop count of 5, like we saw earlier. But now, if we turn debugging off and do a show IP route, now you can see that our RIP domain has been reconverged. So we have successfully configured the MD5 authentication, because we can see that our hop count is back to 2 to get to the 150 network, whereas before you can see that it was set to 5 hops. So again, that's the basics of the RIP routing protocol. We looked at RIP version 2 in this lab, and RIP version 2 authentication and hop count. We explained how RIP uses hop count to find the best path through the network. We showed you some debug commands within RIP. We saw router 2 reconverge to router 7 when we had the link down between R1 and R2, the authentication mismatch. We saw that with the hop count of 5 when we saw that convergence take place with the authentication mismatch. But once we straightened out the authentication between router 2 and router 1 with MD5 authentication, we saw that the hop count went back to 2. So again, thanks for watching the video, and I hope to see you guys in the next video. Thank you.